Hi, welcome to this video in which we will talk about the Fourier transform, and we will continue talking about cosine and sine waves. As we saw last time, we saw how using cosine and sine we can extend our consideration of these from just relating lengths and angles into creating waves. And in today's video we will see how we can use these very essential cosine and sine waves to basically construct any kind of wave or any signal that we might have. This is very generalizable to any field or any application. Anything that has a signal and this signal is progressing in time, it will have a place in this application. So let's try talking about the Fourier transform, and in this one I have created this script in MATLAB, and feel free to read this script and change it, and I will go through this script line by line, and we will see what this script is doing. And I feel like instead of just describing what the Fourier transform is, it's really nice to have this closer look and see a line by line code of how to implement the Fourier transform and the inverse Fourier transform. And also we will try to see this in 3D and interact with the figure to really get this feeling of the Fourier transform and its importance. Okay, so we can actually start by talking very generically about the Fourier transform, and I would say that with the Fourier transform the idea is this: if you have a wave, this wave is having any kind of shape, this wave can be constructed into different sine waves. So basically we can say that we have a sine wave looking like that, and we have another squished sine wave with a higher frequency, and even a higher frequency sine wave like that. And if we add all of these together, we will end up with this point. If we add all of that together, we'll end up with this point, and so on. So we are basically saying, instead of looking at the number 9, we say that 9 equals 3 plus 6. It's something similar to this. And instead of just looking at the value of the wave, you are looking at the main building blocks that were added together to construct this. And of course 9 is harder to look at, but 6 and 3 perhaps are the easier versions to just visualize or just think about. So it's more like that. So the wave itself is looking very complicated, but if you look at the main building blocks of this wave, you will see that it's a summation of different sine waves. These sine waves are happening in different frequencies, so each one of them will have different frequency, and they could have different amplitudes as well. So it will have different amplitudes, frequencies, and even phase shifts. So importantly, again, you have a wave. This wave can be seen as a summation over many sine waves. So this is the main idea. So let's try to see a real example for this and look at this code. Okay, so in this code we will try to build our signal, and with this I am using this script as well that I built, and feel free to check this script. The idea of this script is that I don't normally think that if you are creating a signal, you need to be simulating a signal just using, let's say, sine, cosine, or somehow using the Gaussian noise to add them on the signal. Perhaps you need a lot of freedom, you need complete freedom over your signal. So what I did here is basically I created this function to transform a drawing that you can draw yourself into a signal. So basically you can draw a signal like that, okay, and from this drawing I'm doing a little bit of image processing to look at the value of each pixel, and then I'm determining the locations of the pixels that are darker than the background, and then I'm converting this into actual indices, and then converting this into actual signal with a number of points corresponding to this. So feel free again to check this, and by the way, you can create many signals underneath each other, so feel free to check this function. So yeah, so from this function here I am transforming my drawing into something else, and you can, let's say, let's look at this part and see what kind of drawing do we have. So we have this drawing. I just created this drawing and saved it as PNG, and MATLAB is reading this drawing.png using the function, and then it will convert this into an actual signal. So let's have a look at this. So this is now our signal, and it should have 100 points, okay, and here I'm creating fs, which is the sampling rate, so we would have 100 hertz. This means that we have 100 samples per second, and this is our time vector. So I am defining my signal to go from time 0 to 1 second, and because the sampling rate is 100, then we will be stepping in time by 1 over the sampling rate. So we'll go from 0 and stepping with 1 over the sampling rate until we reach 1 second, just minus a very small fraction, which is 1 over s, because we started from 0 and we need the time vector to match the length of our signal, basically. So the time will be also 100, going from 0 until the end. And by the way, I hope that you have enabled this data type function in MATLAB. If you didn't, please check the first tutorial video on that. And then we go to this one, we create the figure, okay, and then we go ahead and plot our signal. So you can see that this is the signal that we drew by hand, and it's actually now working. Okay, so after that we step right into the transformation, and we start by defining a lot of variables that we will need. So first of all, we just get the length of the signal, which is 100, and the reason for this, we will be creating a complex sine wave. So again, we will be using the sine wave, and we will see what the complex sine wave really is and how it's useful in the Fourier transformation. So here we are trying to normalize the time. So basically, instead of creating the time, our time vector of the complex sine wave as from, let's say, 0 to 10 or anything else, and step by the sampling rate, we want our transformation to be very general. So we don't know what the sampling rate is. We don't care what the sampling rate is. We'll always have this number of frequency points covering the whole signal. So we start from 0 frequency, we end up at n-1 frequency points, and we will be looping on the frequencies. So this is just a normalized time, this is the actual frequency points, and we don't need this, of course, to be dependent as the sampling rate, as we said. So we create this frequency vector, and later on we can transform this into hertz as we will see. So we define another important thing, which is the Nyquist, and I'm putting this just to convert what we are seeing into hertz, but we don't have to do this in this kind of demonstration, because here we are merely demonstrating the Fourier transformation. We don't really need to convert our frequency spectrum and look at hertz on the x-axis and then look at power or something. So but anyway, I'm doing this here because I think it's important to have this in here. So we are defining Nyquist as the sampling rate divided by 2, and it's important to know why we are doing this. I will come to this after this line. And here I am extending from 0 until Nyquist, and I have number of points equals to the length of the signal divided by 2, because we are going from 0 to half the sampling rate, and I am putting +1 because we have 0 frequency, so we have this DC component, so we have one more value on our hertz axis. So let's go to this one and see what is this and what is aliasing, and we can consider that we have our signal looking like that. And basically what we need to do, we need to try to describe our signal using different points. So let's say that we have many points trying to describe the signal. So let's say that we have many points like that trying to describe the signal. If you have many points like that, then you will have a very good estimation of your signal. Okay, so let's now consider that we have a signal, and this signal is oscillating between positive and negative. It's really changing. Then the minimum number that you can use to estimate this signal is basically 2 samples. Why? So let's say that you have your sampling rate covered like this, and you only have 1 point. If your signal is changing that much in this just this very small period, would you be able to catch this change using 1 point, such that you have another point here and then you have a third point here? No, because if you use this to estimate your signal, it will look something like this, and this is what is called aliasing. So you don't recover the original signal, you are changing how it looks like. So if you have a signal and it's oscillating like that, it will be a good idea to have, let's say, a sample here and another sample here to try to catch this change in the signal. So that's why if you have, let's say, 100 samples per second, so if this is 1 second and you have 100 samples in here, you would be able to estimate up until 50 hertz, and anything higher than that will not be something that you can effectively estimate and think about. And this is normally if we go higher than the Nyquist frequency. If this is our frequency spectrum and we have 100 hertz and this is 50, so this is Nyquist. If we go above that, we say that this is a negative frequency, and you would normally, for a real value signal, you would normally see that the spectrum, if it looks like that, then it will be like a perfect mirror of this part of the positive frequency is mirrored here in the negative frequency part as well. And that's coming because if you have if you are spacing your samples further apart and try to estimate the higher frequencies, your signal actually gets slower and slower until it reaches the same shape or the same part that you were estimating when you are trying to get the very low frequency here. Okay, so I know I didn't fully describe everything, and that I'm just trying to cover like the main idea of the Fourier transformation here, and I think it would be nice to look at this with a real example with real values, such that we know what is going on. So in this one, what we basically need to do is that we now know that we are trying to estimate our signal using different waves like that. So for each of these waves, we have a magnitude and we have phase. So if you remember last time, we said that a sine wave is actually coming from a vector just rotating very nicely and safely inside a unit circle, and that's how you can get a sine wave of amplitude 1. And so you can consider this when like we look at the building blocks and see that it has a lot of sine waves added. We can look at these waves in a different way. So we can consider them as each one of them having its own circle, and this circle is different radius, because this depends on the magnitude of the signal, and each one of them is having a vector like so. And what we want to do right now is to know the initial configuration of each one of these waves. So what I mean by that is that we have different waves and we know each one of them has a frequency. So what does it mean that each one of them has a frequency? Okay, so for a frequency equals 1, we basically mean that we have 1 cycle per second. Okay, so for this sine wave, if this sine wave is starting from here and ending here, and this is 1 second, what is going on with this wave? This would mean that this wave started here, ended here, and it created 1 cycle, because after that it's just repeating. So this is 1 cycle. So if we got a signal looking like this and building 1 cycle in 1 second, then this is 1 hertz, because we just look at 1 second and we count how many cycles we have. Okay, so let's have another example here. Okay, so let's say that now we have 1 second and the signal inside the 1 second looks like that. Okay, how many, or what is the frequency of this wave? We can just look at this and we would see that this is 1 wave ending here and the wave is repeating here. So we basically got 2 waves inside of 1 second. We get 2 cycles inside of 1 second, so the frequency is 2. Okay, so we count how many cycles do we have in this 1 second, and so on. You can extend this in whatever manner you would like, but this is how we can read our signals. So we can basically say if this is 1 second, we can like 1, 2, 3, 4, and this is almost 4 hertz. It's like that. So you can now look at any signal and try to estimate, try to determine the oscillating the frequency based on which this wave is oscillating. Okay, so back to our vectors, and I really like to represent them like that, because we now know that our waves are actually vectors, and these vectors are rotating inside this circle. So what makes them look like waves is that we get the value for this one projected on one of our axes, and then we try to proceed with this and try to see the vector when it's here, the vector when it's here, and so on, and project it on our axis, and that's how we can create this wave. And we discussed this and we saw an illustration and animation for this in our previous videos. So we can now consider this shape and say that we have our signals added together to build this wave, and each one of them is actually a rotating vector. So the question is now that what will be the initial configuration for the phase value, and what will be the magnitude for every frequency. So we have established how to get the frequency. So we know that we will go from frequency 0 and we will go up until n minus 1 points, and we can clearly estimate up until the Nyquist frequency, so up until half our sampling rate. So all of that is really nice, but right now, how would we go ahead and estimate this? So we know that this vector is representing frequency, let's say 0, and this one representing frequency 1, and this is 2 hertz, and so on. Or not hertz, uh, any unit. We don't really care about that right now. But we would say that it's hertz because we are looking at how many cycles per second, basically. So for this one, it's 0, so it's not really moving. Okay, so perhaps we can, just to understand this, we can start from 1, and let's say that this is 2, and let's say that this is 3. So what is the meaning of that? This means that this is 1 hertz. So we basically, if we took our vector from here, and this vector rotates all the way on 2 pi, because this is to cover the circumference of the circle, we would need 2 by r, because that's the circumference of this circle. So the thing is, we would need to go 2 by the radius of this. So let's say for something like that, for 1 hertz, we are trying to see how we can go around the circle and end up at the beginning again, and how much time we take for that. So this one tells us this kind of information, because this is 1 hertz. It means that we complete 1 cycle per second. So if we looked at this rotating vector, it will complete this 1 cycle in 1 second. This is the meaning of that. And this vector, if it's starting from here, it will go to the same position in half of a second. Why? Because this is 2 hertz. It means that it's completing 2 cycles. It's completing 2 cycles in 1 second. And this is 3 hertz, so it's completing 3 cycles in 1 second. So it's very quick. Okay, and so on, so on, and so on, if you go higher in frequencies. Okay, and this is the basic idea. So what we need right now is, instead of thinking for these as waves, think of them as vectors. So with vectors, we have very nice formulation that tells us that we can estimate the sine waves as a complex waves. So we basically can use this formulation and see what is going on with it. So it's e to the power 2 by I f t, okay, and this equals the cosine plus I sine, okay, of the same of the angle. Okay, and when we have a magnitude here, the magnitude is multiplied by them. Okay, I'm not gonna go through this in detail. I would just try to get the gist of this. Okay, so I think we know that one of the very nice, very elegant equations in mathematics in general is the Euler formula. It says that e to the power I pi plus 1 equals 0, right? This tells us that if you have e to the power I pi equals, this would be equal to -1. So we can actually put that's the same form. So we can say that it equals -1 because the magnitude here is 1, right? The magnitude here is 1, and we would say that this equals cosine plus I sine of pi, and we know that cosine of pi, so again think about the unit circle. The cosine of pi is what? The cosine of pi, when you go pi and project on the x-axis, because that's the cosine, so cosine pi is -1, okay, plus I sine. What is the I sine? the I sine of pi is, we go and the vector will be here, so the sine will be 0. Yes, so plus 0. So this would equal minus 1. So that's why e to the power I pi would be minus 1. Okay, this is just to understand it visually with the rotating vectors, and I'm just using the equation, nothing more. Okay, so we can think of this very nicely in such a way that says that e to the power I of something is a phase rotation, okay, and we can estimate the cosine and sine of that and get the actual number for this, the actual real number for that. Okay, so why we are mentioning this? We are mentioning this because now we are trying to estimate our signal using a complex sine wave, and that's the formulation of a complex sine wave. It has a cosine and I sine, so it's almost like that. We would have two axes. We would have the real axis, okay, representing cosine, and you have an imaginary axis representing I sine, okay, and you are rotating between this with vectors, and this vector will have a value for the real part and a value for the imaginary part. Okay, so right now back to the Fourier, and let's say what is going on. Okay, so now we knew that if you have a vector and this vector is rotating inside the unit circle or inside the circle, this vector is making a phase value, let's say theta, okay, and it's moving with this theta value, right? And because we have a frequency, we know that this vector is having an actual angular speed, so it's really rotating and having a specific speed of rotation. And then we can consider something else. What will happen if we try to estimate the initial magnitude and phase of this? And the idea is that in the Fourier transform we would need to estimate the initial configuration of each of these signals, because the signals will have, as I said, perhaps different amplitudes and different frequencies and phase as well. So what we need to do, we need to know the initial configuration of this vector, the initial configuration of this one, and all the frequencies, and we will store this information, and we will say that these are the Fourier coefficients, such that we will have a vector value, a complex value, multiplied by e to the power of I, then the theta or the phase. The thing is, we would need a magnitude and the phase, and we know the frequency that we are estimating. So we are basically storing each one of these vectors, and that's how we go to the frequency domain. That's the frequency domain, okay, because for each frequency you know your magnitude, you have a phase value, and you can extract the power by just squaring the magnitude. So it's very important to know this. Why? With this, you are compressing the information of the signal in the frequencies. Okay, so you are basically doing this lossless transformation, and you are not losing anything because you are having all the frequencies. And here you can analyze your signal in the frequency domain and try to know more dynamics and try to extract more features and know a lot of characteristics that you wouldn't be able to catch by eye or even some algorithms in the time domain. So it's very important to look at the frequency domain. Okay, of course it depends on the application. In some applications you will just look at the time domain, some applications you will only need to look at the frequency domain, some will take features from both. But the thing is, it's very nice to have this in the frequency domain, and it's a lossless transformation. So back to the point, now we have vectors, each one of them oscillating or rotating with a specific frequency. Right now we need to do the opposite. We need to recover our signal. Okay, this is the inverse Fourier transform. So what will happen then is that, okay, you have your vector, you know the magnitude, you know the initial phase. To recover your signal, what you need to do, you need to rotate these vectors and add them together, because when you rotate this vector you will get this wave, when you rotate this vector you will get this wave, and so on for all other frequencies, and then you just add them together. So to do the inverse Fourier transform, you will get the coefficients, which are the vectors that you have, the complex vectors that you have, and then you just rotate them and then you add them together. Okay, so back to the Fourier transform, we would in the beginning try to estimate the initial phase and try to estimate the magnitude of our vector. Okay, and with the inverse we will just set them rotating, nothing more. We will rotate them and add them. Okay, so with the Fourier transform we will try to stop each frequency. It's a little bit weird, but this is what is happening, because let's say that for this one 2 pi a f t, if this is 1, if this is 1 second, if this is 1 second, okay, and your frequency is 1, then what is happening? This would mean in 1 second you will be completing 2 pi, because this is 1 and this is 1 and this is 2 pi, okay, and this is I, so it will be a rotation, as we said, e to the power 2 pi, or I theta is a phase rotation by this theta, so here we are rotating by 2 pi. So for a frequency 1 you are rotating by 2 pi. Okay, so what would you need in order to stop this vector from rotating? Because if you stop this vector from rotating, this would mean that you are still rotating all other frequencies, but the important thing is if you add all of them together, if you add the values of the vectors together, it will be not affecting your summation, it will be only estimating the frequency that you have stopped. Okay, so we basically need to see what kind of frequency we need to estimate, and then we will just do a very simple thing. So what we will do after that, we will just put a minus sign to this, and that's how we stop this frequency. We stop this vector from rotating. So if we put a minus sign to this and we estimate our vectors, okay, and then we look at the similarity, almost at the similarity, because we will be doing a dot product between each one of these waves. So each one of these waves, as we said, has a particular frequency. So if you multiply this one by this one, element by element, and then add them, you will see almost the contribution of this frequency into this signal. Okay, so the first step is to basically stop the frequency that you want. Okay, so all of the other frequencies will not matter right now, and let's say that we are estimating frequency 0. If you are estimating frequency 0, you would say that you don't need to do any phase shift, and this is right, and then all of this will go to 0, so all of this will be 1, and it will be almost as if we are taking the average of the signal, because then it will be all 1, and 1 multiplied by this signal element by element is like we are summing over the signal, and then we will be normalizing by how many multiplications that we have done, because other than that it will be a very high value that does not represent the magnitude of the signal, but we need to stay in the same like scaling. That's why we are normalizing by 1 over n, because we don't need this to be a very high summation. Other than that, if you don't do this, it will be like in like 3000 or something like that. It will be very, very high values for the spectrum that you will get. Okay, so again, we stop the frequency, we stop that frequency, and then we try to estimate its contribution basically. So we see its similarity with our wave, and that's the coefficient That's the coefficient, that's the initial configuration of this vector. The first coefficient, let's say, will have a magnitude like that, and it will have this phase. Of course, the magnitude will remain the same no matter how we rotate this. Okay, so we get the initial configuration of this and this one as well, the initial phase, and we get the magnitude and all of them, and these are stored in this variable coefficient. Okay, so perhaps you can go now on the code and run all of this to see we will have 100 coefficients, as we said, and each one of them is a complex value. So a complex value here has a real part and imaginary part, and we can get the magnitude and phase from that vector. Okay, as we said, we will normalize them. Here I'm just doing some steps to get this in the same scaling as the magnitude. So I'm basically taking the absolute of our coefficients, okay, and then I'm doing this to get the magnitude so that we get the absolute, and then we just double the positive frequencies. As we said, we wouldn't be looking at the negative frequencies, so the part that we explained here, so we wouldn't be looking at the negative frequencies. So what we do, we take the positive frequencies and we double them basically. And I'm starting here from 2 because the first one is 0 Hertz, so it's not really a positive frequency, so I wouldn't double it, so that we end up with the actual spectrum of the signal. Okay, so it will look something like that. It will look something like that, okay? And then we can recover our signal. So the basic idea is to take this vector, each of these vectors with its particular frequency. So I'm looping over the frequencies a second time and taking this vector, and then what I'm doing here is basically for each frequency I am rotating its vector. As we said here, we will be getting after getting these vectors, we just need to rotate them each with its corresponding speed. So that's what I'm doing here, e to the power pi I. As we said here, that's how we rotate our vector, but this time this will be positive because we're not stopping or doing any estimation anymore, we're just rotating this vector. So it will be e to the power 2 pi I ft. T is the normalized time, it's fine, and the frequency that we are looping on. Okay, and then we are summing them. So here it's the first step that we said, because we are doing this for each frequency. So for each frequency we will be rotating all of this, so it will be creating the whole signal for a particular frequency, and then we would need to add all of these together to reconstruct our signal. So that's what we are doing here. We are taking this, it's the first one, and then we are adding this to the second frequency, and so on. We loop over the frequencies, we add all of the signals together. So we are adding all of this together to reconstruct our signal. And let's look at this. When it ends, we can either look at the real part or the imaginary part, but of course our signal was real, so it's a real value signal. We don't really have an imaginary part, so it's almost like our vectors. If we have a real and imaginary axis, like this, then our signal is not leaving the real axis because there is no imaginary value. So it's like our vectors are only rotating here and not leaving the x-axis. Okay, and whenever they are having like an end tip or the end effector of this combined rotations, we have a value for our signal. So when it moves here, our signal produces this point, moves there, this point, and this is how we will estimate the signal. We will look at an animation for this. I know it's not very clear right now, but we will look at an animation for that. What we need to know is that we are looking at the real part of the signal, because this is a real signal, and we are estimating the signal again. We are trying to recover our signal. If you remember, this is the shape of our signal, so it looked like that, and what we will estimate right now is the reconstructed version of our signal, and we can see that it's exactly the same signal. So right now we will try to do something else, and I think it's very interesting. We will try to visualize the vectors, visualize these rotating vectors, and see them at every time instant.